dogs, and the experiment and the BPM model is a bit complex for regression. And but we try to avoid this overfitting by including different heartbeats from the same dog. And but I think the result is still a little bit overfitting. That's why in the later parts we use this SIGA model to try to avoid this. Yeah.
Okay, thank you. But is it not that more complex model requires more parameter, so you can it's more prone to overfitting?
Yeah, I think for the BPM model is very easy to be overfitting, but for the SIGA model, it's actually first designed for the image segmentation. So for the input and the output, they are the same image, but for the output is segmented image. And it also performed very well in the clinical side, and it also for the result is good based on small data set, and also for my data set is also a small, not very large. So I think for the SIGA model, it's not that possible for the overfitting.
Yeah. Okay, thank you. The second question I have is about proposition number 5. So if I may ask one of the paranymph to read it.
The nice thing about standards is that there are so many of them to choose from. Andrew as standard.
Thank you. Here comes my question. Does having many standards contradicts the very idea of having a standard? The more standards you have, the less standards there are. Can you please comment on this?
You mean the standardization of the 2D figure?
No, having many standards. So if you have many standards, it means that neither of them is actually a standard.
Yeah, actually for the 2D standardized mapping here, we try to make the shape of the 2D map we can standardize, but actually in the potential map, I mean the 2D potential map, this standardization is not that hard because we try to include the differences of between different maps by showing this how this signal distributed on this 2D map. So the shape is standardized, but the potential is not. The pattern is not standardized.
Thank you. And if you would generalize this to more, let's say, overall case, would you still recommend having many standards, or would you advocate for having just one standard? Do you agree with this statement?
I think for me, I can just include the standardization actually to some extent, but I won't do it too much. Yeah.
Okay. Given the time, I give the word to the prorector.
Thank you. The opposition will be continued by Professor Dr. Jost Lummens.
Thank you, dear prorector. And dear candidate, I really enjoyed reading your thesis and assessing it. It's a great example of addressing very relevant clinical issues of a new technology with technology. My compliments for that. And it's a day of pride, of course, for you and your beloved ones, but also for your supervisory team. You can see that you could build on a solid fundament here. Congratulations. I want to, with you, to reflect on the following, and that is that you address two critical and relevant approaches to problems of the inverse problem, or problems, challenges. The one is the ill-postness. And you investigated the regularization, and which actually fundamentally requires accurate geometric information. The other one, very relevant, is that, hey, let's investigate whether we can skip the imaging or do without it, which, in my opinion, does not really help you in stabilizing the ill-postness problem. Huh? So could you reflect on this apparent tension between those objectives and explain how these two approaches can be reconciled, maybe?
Okay, highly esteemed opponent, thank you for your nice compliments and questions. So I think you just asked how for the second project, how I can simplify the process, because it seems I don't do something that can make this ECGI more accessible, right?
Well, yeah, you need the imaging in the first issue, so chapter 2, and then you say, well, regularization is very useful. It doesn't even matter how we don't have to tweak the lambda, the parameter. And then in the second, you say, well, let's investigate if we can get rid of the. I can imagine that does not improve your ill-postness.
Oh, yeah, okay. So yes,
how can we combine? How can we get to both together?
Yes, I think for the deep learning project is actually the project. The experiment is based on the ECGI process, so we can kind of also include the ill-postness of the inverse problem. But we don't want to kind of replace the whole ECGI process totally. And it's just kind of before the more complex ECGI process, we can just do this deep learning framework. So if the phenomenon on the heart is fine, then we don't need to do the ECGI. But maybe if something very weird happens on the heart surface, maybe we can do more complex ECGI as a second step. And as for this ill-postness, actually, for this deep learning framework, we are not dealing with this part. But I mean, for this deep learning framework, it's only the kind of our initial experiments. But I mean, also for my further project, I think in the future, I can also try to eliminate the ill-postness in the deep learning framework by include other parameters kind of to just improve this deep learning framework a bit.
So I try to summarize. I'm not a true expert in this field, okay. So my apologies for that. But so you're basically saying that you enable different approaches of the same problem depending on the purpose of it, isn't it? A more precise, accurate way, maybe with imaging, and a more coarse way without.
You mean I can use different methods for the deep learning model or for the deep learning framework, or right?
No, well, maybe I was thinking the context of use may have changed, because if you don't use the imaging, well, you accept certain inaccuracies at small level, I guess, I would say.
Yeah.
Then a final question, but it relates to this. So you nicely show that this lambda can work well for different beats and subjects, just one value. That's quite nice. It's easy. What does this actually tell us about the nature of regularization in ECGI? So if there is one value that you can use, and if you change it, it means that the solution is not very sensitive to it. Or am I wrong?
Yes, I think because I'm using the doc data for the experiments and also see some results in the hospital from my colleagues, they also share me some data. So when I see compared to the lambda on their data sets, the value is all around 0.01. Yeah. So I think it's because for this whole ECGI process, we use different methods to solve this inverse problem. For example, we use the boundary element method, but in other groups, they maybe use the fundamental method kind of to solve this whole ECGI process. But at least, in Maastricht, we are using a very typical, a very classical process to solve this ECGI process, and it shows that both in my faculty, also in the hospital, the value are all around 0.01. But if we want to solve this whole ECGI process using different mathematical methods, maybe this value will be different. Yeah.
But I'm just asking myself, and also you now, is what does this mean that it's always around 1, 0? Does it mean we maybe it reflects limitations in how we actually currently evaluate the quality of ECGI maps? Maybe that's a suggestion. I don't know, but
I think at least it can show us, based on this typical method we use to solve this ECGI, is already sufficient for to use this fixed regularization parameter value. So it can solve the euposterness, but it's enough to just use this fixed value to solve the euposterness. But I mean, in other dataset, or if we want to use other typical method, maybe you can also use a fixed method, a fixed value, but the fixed value might be a bit different. So this fixed value can solve the euposterness also, yeah.
Okay, thank you. Do I still have something? Yes, 1 minute maybe. May I ask one of the partners to read proposition number 6 in the microphone, please, because there are people online probably.
A well-trained deep learning model can facilitate ongoing monitoring and testing, enabling personalized treatment plans. Impact.
Thank you. Can you briefly explain what is meant with well-trained?
Well-trained, I think you can also see the result in the chapter 4 where we try, chapter 4 where we try the sequential SIGAM model. Here we include the time window here. And the result from the potential map, also from the electrogram, the results also perform very good. Because we include the novel human data, so the geometry are not used during the test, during the training. And the result is good, so for the novel subject, so that's when we can call this network is trained well, because it performs well for the novel data. So this is well trained.
Perfect. Yeah. Thank you. I thank you for your answers, and I give the word back to the prorector.
Thank you for your questions. The opposition will be continued by our online opponent, Dr. Laura Beer.
Thank you very much. I'm very sorry that I can't be there in person with you today, but Tiantian, I just wanted to say that it was a real pleasure to read your thesis and see the very impressive body of work that you've done for it, and the very broad range of work that you've done. So I just have a couple of questions. So the first is in terms of the study on the regularization parameter. So we saw that you used several different metrics to evaluate the changes, and as used to mention, the changes that you saw were very small, depending on the regularization parameter. However, from my own experience, I've found that some of these metrics can be insensitive to meaningful changes, I mean clinically significant changes. So I was wondering, did you look carefully at the electrograms or the activation times themselves to see if there are any clinically relevant changes with the different regularization parameters, such as changes in the presence of artificial line of block?
Yeah, esteemed opponent, thank you for your question. Actually, I didn't catch your question very clearly, so could you please repeat it, maybe?
Sorry. You saw that there were not very big changes in the different metrics that you used to compare your electrograms in the regularization study. I was wondering, did you look at the electrograms and the activation times on a one-to-one basis to see if there were any clinically relevant changes with the different regularization parameters?
Yeah. Actually, I still didn't catch it. Sorry.
And so as you changed your regularization parameters, did you look at the electrograms themselves and see any changes that were clinically relevant?
Yes, when I changed the regularization parameter, I also compared the activation time again also. Yeah.
Yeah, and in those activation times, did you see any changes with the regularization parameter that might not be shown with the correlation coefficient, for example, like changes in line of block?
Yes, for the activation time, I think I only show it when I compared it with the fixed value, also the other methods. But when I analyze the wide range of this regularization parameter value, I didn't show this activation time map actually. But I think from this kind of the box plot is already sufficient enough to show that the value it can perform well. Yeah.
Okay, so that's what I was saying. So the correlation coefficient or the mean absolute error can be insensitive to certain clinically relevant changes. So I was curious, did you look at the activation maps themselves to see if there were any significant changes by eye?
Okay. Yes, here actually maybe we can use as a future thing, but here we only use the show the electrograms actually. Yes, and not the 2D map. Yeah.
Okay. In terms of the deep learning based methods, then it would seem that a lot of the data was interpolated at the body surface and at the heart surface with the pre-treatment that you did of the signals. We've learned from ECGI to avoid interpolation if possible because it can introduce a lot of errors. I was wondering if you've thought of a way that you could assess the impact of interpolation and the error that would introduce with your deep learning based methods.
Sorry, can you repeat again?
How would you design a study to assess the impact of interpolation error on your deep learning model?
Impact of the interpolation method. So for the deep learning model, right, I do the interpolation to generate these 2D HSPM and BSPM. And actually, I think in chapter 4, we already show the original, for example, the body surface electrodes with the recordings and the heart surface potentials with mesh points. And we compare this 2D map with the interpolated results. So it shows that these body surface recordings and also the heart surface potentials based on the mesh points are very similar to the interpolation methods, the maps generated from these interpolation methods. And while doing this interpolation, we also try two different interpolation methods. And for the second one is based on this 3D heart geometry information. So we try to increase the precision of these interpolation methods, yeah. And we also believe it's quite similar to the previous ones.
Okay, so you think interpolation did not have much impact on the results?
Oh.
Okay.
Yeah.
I have one final question, if I have time. So your current implementation reconstructs the epicardial potentials themselves. Could you think of a way that you could incorporate potentially essential septal or endocardial information to reconstruct the endocardial surface?
Yes, okay. So your question is, now we only include the epicardial potentials, but maybe for the we can only also include the endocardium kind of potentials, right? Yes. So best in our data set, actually, we only have these epicardial potentials, but also I think endocardium is also very important. I think I also want to see it as one of my directions in the future research to include, maybe even for the 2D atrial mapping, I also want to include the fiber arrangement for this kind of thing to generation. Yeah.
Okay. Thank you. Thank you very much.
Thank you.
Thank you for your questions. The opposition will be continued by Dr. Peter van Dam.
Thank you for your wonderful work. Indeed, a pleasure to read it. And this mathematical approach I love too. And it's about my hobby, so that's anyhow good. You use deep learning framework to learn basically ECGI. But ECGI is a very complex interplay between measurements and the model you use, for which some feeling, which is not very scientific, but for realistic, physiologically realistic, let's say, interpretation is needed. What you have done in your work is basically trained your model to recreate the inverse solutions that were by one model created, and you could use, I think, many others. I use an inverse with septum, so you could use also that one. But would it be possible, and do you have, and this is more philosophical, what kind of data could you use to say this is a physiological, reasonable solution, instead of taking a physician or me looking endless at maps and saying this is realistic and this is not, but that's not objective? What kind of information, because a neural network or AI could use any information, what kind of information would you want to use in that sense?
Actually, for the information more related to the data itself, I think if we want to use it widely in clinical science, the information doesn't matter too much, because if you have very big difference about the information across different subjects, maybe the deep learning framework can't perform very well, then we can't trust it. So I think from my side, at least when we want to use it in clinical side, not only in the scientific side, we need to also discuss it with the clinicians, to make sure what kind of data information we need and what kind of data information will have a big impact for this performance And as for data itself, I think currently we only need this geometry thing or the recordings thing. So as long as we can maintain that we can get the good geometry, we can get the good recordings or correct recordings. It doesn't matter that much if we want to use the framework. Yeah.
But I would like to use the framework to outperform the clinician.
Oh, okay.
What would we need there?
Yeah.
Because we can, of course, we need to ask the clinician what is relevant. But if you take endocardial maps from Carto or Nefix, that's the truth. Well, if you start using them, it's not. Then you have to merge them. So, and on the other hand, there's just myocardium with physiological parameters. It has a certain connection. We know something about scar. You have already been using others. What kind of information could we use there?
I think for this current project I already did is a very good point for further, how to use and what kind of information can be used in clinical side, because now it's only very simple information here. But actually especially in the clinical side or the physiological information here, I think because my clinical knowledge is very limited, so I think from my side also maybe the size of the subject or the patient may be also needed in order to obtain the more precise torso geometry or to make the deep learning framework perform better. This is one thing. Before I also discussed with my supervisors, so we think it will be also better to include the torso size or maybe the gender yeah. But it's only very initial thinking ideas, but we still need to more discuss about it.
At least you get enthusiastic about it. That's already a very good sign. Yeah. My second question is about making the atria 2D. You used, which I really love, just the approach already making an image-to-image inverse, let's say. That concept is really nice. The input is segments, which you took from others. How important are these segments? Would another segmentation deliver something else? One of the things that I thought of was clinically already relevant. How much percentage does a certain segment contain? Because some atria are huge on the left or on the right or on both. How much relative tissue is there? That's already clinically relevant. That you didn't even write up, I think, but it's already there in your paper. But if I create a different segmentation, if I want to separate it in a different way, how different do the maps look like?
Yeah, I think because for the current 2D map for the deep learning framework, we only segment into right part and the left part. We don't do very detailed segmentation. So this is only for this experiment, for this data set. I think also only for this unique deep learning framework or deep learning model. So if we want to use one model, we need to make, on the one hand, we need to make sure that all the segmentation across these whole subjects are the same. Then we can trust this deep learning model if we want to use this model for the novel subject, but also the same segmentation. But if we want to include lots of subjects with different segmentation, and we still want to use the same network or the same model, it is a bit hard, I think. So I think for me, if I want to include the segmentation for the same data set, I will try to include the same segmentation. Maybe for the further, try different segmentation, but I won't make it too complex because the deep learning framework maybe can't catch it very well. Yeah.
Would it be an option to make this segment smaller if the right side is smaller? Would the framework still handle that?
Then if the right side is a bit smaller, then for the left side is a bit bigger. Then for this figure, maybe it's not a full square kind of, a full rectangular. But I think if we want to do it, we need to leave some white boundaries maybe for the right atrium. But we need to make sure that for the whole data set, it remains the same. Then the model can remember, oh, there is a white boundaries around the right atrium for all the subjects. But if we only want to include this white boundary, maybe for several subjects across this whole data set, maybe it's a bit tricky for the network to learn how to learn it. Yeah.
Thank you. Nice answer. I will give the word back.
Thank you for your questions. The opposition will be continued by Professor Dr. Li Baumann.
Thank you very much. First of all, I would like to compliment you on a very interesting and extensive thesis. And of course, these compliments not only are regarded to you, but also to the entire promotion team. Furthermore, I thought I saw, did you do the drawing yourself?
Yes.
Yes. So as a vascular surgeon, this of course makes my heart beat faster. So compliments also on the illustration, which leads me to the next questions. And what I'm going to do is I'm going to take you a little bit out of your comfort zone, because the previous speaker already said about overdoing clinicians, and I am a clinician, so I have to be very careful here. Because I'd like you to take you to page 131, in which you discuss at least the 3D geometry to standardize 2D mapping.
Yeah.
And what you do is you take 64 electrodes, and you get the data out of that to get the torso geometry. And this subject was briefly catched, but if you are measuring patients, there is a very large variability. So can you think of any patient confounding variables that you could think of that might influence your data, maybe, or data collection?
I think it's a highly esteemed opponent. Thank you for your nice compliments and questions. So for I think it's really similar to previous question. Also, I can try to include the torso size and the gender kind of. And also, in order to increase the precision of the 2D map, I think we also it will be good if we can include other layer of the heart. So the signal propagation will be more precise compared to the current one.
So just being a physician and not knowing all the very data and the mathematic stuff you did, could, for instance, a body mass index influence your readings? Or we know, for instance, that we've got patients with a pectum excavatum, which is a sunken chest, or people with a coronatum, which is a funnel chest. Could that, for instance, influence the data collection and ruin all the mapping?
Yes, I think to some extent, if only use the current wording, I think it will also influence the kind of the body surface electrodes kind of.
Okay, and on that question, what because I do a lot of MRIs and a lot of CTs. Why wouldn't you combine this part of data collection and visualization with, for instance, computer tomography or an MRI? Or why wouldn't you combine it?
Because as I said before, the MRI is time-consuming and costly, and CTs can introduce some radiation. So that's why we tend to get rid of this part. But I think because now it's not, you just use this deep learning in clinical side, you don't need to rephrase it anymore. So to some extent, I think if we want to still work on it, you can try to combine the MRI as a tool for the further studies, for further research. But our final goal is we want to get rid of this part, but maybe in the middle part, we can use it as a tool.
Yeah, because I think the combination of in the clinics, of course, sometimes you do both. You say I want a CT and I want an MRI, and perhaps I like an ECGI, just to combine and make all the parts of the puzzle stick together.
Yeah.
So maybe that could very well be. What I also thought about, and this is looking from a purely clinical point of view. In page 34, you do very nice study, but what you use is anesthetized dogs. And in the clinic, when we do a regular ECG, and we have a patient move, then that's your ECG gone. You'll have to make a new one because they only have to move a little bit. Now you use anesthetized dogs and you put up to 216 electrodes on that animal. And we only use 12, 10, 12, 3, it all depends which ECG you use. But how could I do that with a patient in outpatient clinic? That's very difficult, I think.
Yeah. For my just imagination, I mean, for current ECG, when we go to the hospital, we just lie down the table and the clinicians just put some electrodes on the body surface. But I mean, for the ECGI, if we want to use it in clinical side, also based on the deep learning framework, without using the MR, I mean, if I go to the hospital, I can just stand somewhere and the cameras around me can make the picture for me about to obtain the total geometry information. And the patients need to wear a vest. The vest can be very loose or very tight, depends on you're big or small, I mean. Then on the other side of the computers, maybe the clinicians can already get the video or what is happening on your 3D heart. So it's kind of the imagination, I mean, so the clinicians can get this short video or they can just get some snapshot to for the diagnosis. Yeah.
Yeah. So although the method is very, very good, we have to have some practical things we have to think of. I'm not too sure if I've got another for a short one. So maybe somebody could read Proposition 7 again in the microphone because we've got online viewers.
In real-world medical applications, clinical human data is a strict yet loving math teacher.
Okay, this of course is your proposition, and perhaps you could explain me what you really mean with this proposition.
Okay, By using these strict, using the clinical human data is very strict. It's very strict because for this deep learning framework, we first use the dog data, but our final goal is we want to use it in clinical side. Clinical side is the work of course human, so our final goal is the human data, so it's strict. But loving here is because our results can show good results. Perform well on our human data. So if the results are good, then it's loving.
And you're doing research on the cutting edge of basic research and clinical implementation. Which is very, very difficult research to do. Because you've got two worlds trying to speak to each other, which is always very, very difficult. And you produce tremendous amounts of data. And I'm going to rephrase this from a professor, a Chicago professor, University, Dr. Kors, and he says, if you torture your data long enough, it will confess you to what you like.
Yeah, I know.
Huh?
Yeah.
And if you take big data and deep learning, which is for clinicians, for instance, very, very elusive, it's very difficult for us to understand. You've got a very large responsibility to do that very, very, very carefully, because it can go anywhere if you don't interpret it right.
Yeah.
And on that bombshell, I'd like to return the floor.
Thank you for your questions. The opposition will be continued by Dr. Nguyen.
Yes, thank you, Pro-Rector. Dear candidate, first I would like to congratulate you and also your supervisory team for this very nice PhD thesis. And Professor Bauman's heart beats fast after seeing those vessels. My heart beats fast after seeing all these electroanatomical maps, because I, as a physician who is really going to dedicate myself to invasive cardiac electrophysiology, this is something that I really like. I see a lot of, as a physician, I see a lot of potential in your techniques to visualize electrical activation of the heart completely non-invasively. And if I understand it correctly, the first chapters of your thesis focus on addressing and optimizing the inverse problem by studying regularization methods and also by implementing a deep learning network. But then in chapter 5, near the end of your work, you explore two-dimensional visualization of the heart to represent the 3D geometries in a standardized way. And as a simple clinician, I can't help but notice that this process seems to involve converting two-dimensional data, like body surface potential measurements and ECGs, into a three-dimensional model, and then converting the three-dimensional model back to two-dimensional representation. So my first question is it truly necessary to go through this process of inverse modeling and back to a forward three-dimensional representation again? Or is a three-dimensional representation of the body surface potential data sufficient?
So you're asking, esteemed opponent, thank you for your questions. So you're asking about, I start from the 3D and then to the 2D and then to the deep learning framework, then again to the 2D and 3D is kind of...
Correct.
Yeah.
Yes.
So it's too maybe complex, kind of, right? I can directly use this 3D maybe.
Yes, you make it very complex and then you make it very simple again. So why don't you just use a simple measurement method?
Yes, the very initial story is actually I want to use the deep learning framework, and when I see the potential map and when I talk to my colleague, my first idea is, they are images. So for those current research, they are just using the 2D images for most of the deep learning model actually. So it's my first during the whole project, it's my first idea to turn it into 2D, standardized 2D actually. But during this whole, I just continue to work on this, but during the research progress, I also noticed that some people also work on the 3D, but actually their 3D study is not that good because they use the old data in the training. This means the training and the testing, they use the same subject. So sometimes the overfitting is a bit big. So I think for the deep learning from the model, it will be very hard if they use this 3D geometry also. And if the 3D geometry is not standardized, which means we need to include lots of subjects, try to improve the performance of the network.
But the idea, I think, from 3D representation of data is to personalize. To personalize it, and then you depersonalize it actually by putting it back in a two-dimensional geometry.
Actually, I think for the 3D, the personalized 3D geometry is very hard for the deep learning to learn because the data is very limited. For the current 2D map, although it's standardized, but we try to include the subject-specific information through the signal pattern. So even though the shape are the same, but different people have different propagation. So it will be inflected through this signal propagation pattern.
Okay, I understand. And then more thinking about clinical application, when do you think these really patient-tailored 3D geometries are necessary? And when is a 2D representation or only actually a body surface potential measurement sufficient? For what kind of applications?
Yeah, I think if we want to get the hard surface potentials, it depends on what information you need for the heart. Maybe sometimes if you only need very general thing, maybe the 2D is already sufficient. But if the clinicians want to get a very detailed and correct thing, maybe you need to do very detailed segmentation and then map it back into the 3D. And also the 2D thing, I think it not only for the deep learning, but also it's a very efficient and straightforward tool for the visualization in clinical site, because you can see all the thing in one view, just like the bullseye plot. Yeah.
I agree. Do I still have time for one question? Yes? Oh, okay. Okay, then I'll just continue. And now, thinking about clinical timescales. So, I prefer your 2D representation, because I think if you use that 2D representation, you really have more potential to implement your technique in widespread clinical practice. And I wonder, how long does it take for your deep learning model to convert these body surface potential measurements into this 2D representation? And the second question is, we now use about 200 body surface potential measurements, but are like 20 electrodes also sufficient to get a similar 2D map?
Okay, so the second question maybe first. So I think current we just used more than 200, but we didn't test for maybe 20 electrodes, but it is also a way we can do in the future, because if we can try to interpolate maybe a large 200 electrodes based on this 2000, this is also fine, but
you may just finish your sentence.
Oh, okay. I mean, so for the first question, I think a little bit forgot already. But
clinical time skills in converting the body surface potential measurements to your 2D model. How long does it take?
It's the real time.
Real time.
Yeah.
That's very good.
Yeah. Okay.
Yeah. I'm very satisfied with the answers.
Thank you. Thank you for your questions. Tiantian Wang, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberation and our return in this room.
All right.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. The mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. To the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Tiantian Wang. The degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Peters is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
All right, please.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible? That's the right answer. Very good. By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Tiantian Wang, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dear Tiantian, it's a great pleasure to congratulate you with the PhD degree you just received. Very well done and very well deserved. And of course, I would like to also extend my congratulations to your family. First of all, to your husband here present on the first row, but also to your relatives and friends who may have been watching you and your defense online. They all should be very proud of you today. Let me shine a bit of light on the journey that brought you here today. 6 years ago, in November 2018, you contacted me and expressing your interest in doing a PhD project here in Maastricht. And it preferably should involve applied mathematics. That is the background. You had studied that at Liaoning University, Technical University, I should say. And you also would love to work on a medical topic. And well, I happen to have some ideas ready, and we have the contacts here with long-standing collaboration with cardiology in Maastricht. And so what we did is, well, I involved my colleagues here, the two co-promoters that you also have here today, Joël Karel and Pietro Bonizzi. We wrote a project proposal, and you submitted it, and then it got granted by the Chinese Scholarship Council, and you arrived here to start on the project in September 2019. And everything looked bright, and you were just getting settled, and we were a couple of months on the way, and then suddenly the whole world changed. There was a pandemic. And yeah, there were lockdowns, and I guess for you, but also for your family back in China, this was certainly not an easy thing to have. And it affected a bit your project in the sense that it was very difficult to connect to the cardiology world because the hospital was doing all kind of other things and had other priorities. And for you, it also meant it took a long time before you could travel back to China. And that continued well into 2021, in fact. And then after more than 2 years, you managed to travel back and to your family and friends. And I remember that even then, in those days, it still took you like 3 weeks of quarantine before you were finally moving free again. But meanwhile, you got over that and your project had started to gain momentum. And even before you traveled back to China, you went with us to a conference in September 2021 at a Computing in Cardiology conference in Brno in Czechia. And there you could present your work to a big audience as a poster, and you got quite a bit of response to it. And we also met Maria Guillem from Valencia there. And with her we discussed opportunities for you to go for a research visit and in Valencia to work with her. And it did happen. So in the summer of 2021, for 3 months you went to Valencia. And well, actually led to a very nice journal publication, which is chapter 5, the work on the atria that you saw today. And then you started, meanwhile, working on the deep learning approach that also is featuring very much in chapters 3 and 4 of your thesis, where the idea is to facilitate something that looks really like the ECGI, the electrocardiographic imaging, but without the need of capturing the heart torso geometry with extensive scanning. And you managed to make this work, and that is something which I think you cannot, people should not underestimate, because it's really a difficult thing to do, and it became the central topic of your thesis. And that was exactly as you had originally planned, and I must say this is not something that always works in every project. Usually projects drift quite a bit around the topic you start with. But you managed to stay on track there. And, well, in 2023, all the work was done, and it just needed some more final writing and polishing, and that is what you did in the last year while you were back in China. Dr. Tiantian, you've managed to pull this off. You've shown great dedication along the way, and you've also grown a lot as a researcher. And I think today we could already see that. There's lots of difficult questions you got, and you tried to handle them really well. You've been a pleasure to work with, always in good spirits and with humor, and these are great qualities also for a researcher, I would say. And you've also married this year, and yes, you sent us spectacular pictures. I guess many of the colleagues will love to see them. And you will continue now on a postdoc position in China. And I can safely say also on behalf of Joel and Pietro that we are sure that there is a really bright future ahead of you. So to conclude, I would like to thank everyone who contributed to this research and this event today. A special thank you, of course, to our guests from elsewhere, Dr. Baer, with us from France, and Dr. Van Dam, and also to the committee members from Maastricht, Professor Lumens, Baumann, Wilbeek, and Dr. Nguyen, for all the effort you put in and for the interesting discussions we had this morning at this event. And thank you to the pro-rector, Professor Weiss, for leading the ceremony. So once again, my warm congratulations. Dr. Tiantian, I think it's time to celebrate, I've said.
Thank you for this nice laudation. Also on behalf of Maastricht University, I congratulate you with the degree you have acquired. I also would like to extend my congratulations to the supervisory team. Great job, well done. Last but not least, I would like to give the online opponent, Dr. Laura Baer, the opportunity to congratulate you.
Oh. Yes, congratulations, Tiantian. I might leave it at that because I know the audio is not very good. Thank you.
Okay, so thanks. Herewith I close this ceremony. This was the official part. The committee and you and the online opponent will take a picture now in this room and another picture outside at the staircase without the online opponent. Meanwhile, the audience can go to the rafter where the reception takes place. Thank you.
All right, please.
don't forget the thesis if you want.
Yeah, I will pick it up after the photo. You wanna? Okay, let's have it.